Does that, okay, that's great. So, right. So, let's see. Right. So what is interesting here? So here's an idea. This is just an example of how you might validate another way of validating that your rules are correct. Here we're just going to define a function that takes a list of characters and copies it verbatim into the precise pattern that would match it, right? And then we can show once and for all that this property holds, although we're going to do it on a concrete list here. So we're going to say, what does this function expand out to? It's just going to be app char1, app char2, app char3, app empty string, or empty string on the end. So we can show that this is going to work, that these values are included in the relation by just applying the constructors over and over again. I don't think there's anything too interesting there to go into. Here's a much more interesting example of something you might want to validate about your about this relation. Okay, so what does this say in English? This says for any string and some regular expression, if that string matches that regular expression, if the regular expression matches the string, well, either way, it must be the case that that string also matches any number of repetitions of that regular expression, right? Okay. And so why is this an interesting property to prove? Again, recall that when we wrote down these rules, we could have gotten it wrong. There could have been a typo, right? We might have forgotten to include a root we actually wanted. So at some level, it makes sense to step back and actually write a couple lemmas about that actually verify that the things you expect to be in this inductively defined data type are what you expect, right? The things you expect to be in there are actually in there, and that these rules conform with your internal sort of your internal notion of what this property is, what properties this relation is supposed to be establishing, right? And this is a reasonable sanity check. Because, again, coq doesn't check anything about these inductively defined propositions, right? It's relying on you to give it good information or a good specification. It just makes sure that they're syntactically well-formed. Yep, okay. I won't say anything more about that. So let's see an example of that in action. Let's see, m star 1. So how is this going to work? Well, intros, as we would expect. App nil r. I guess we proved this, this lemma before, that we can always append nil to the end of the list. That's what we're going to do here. And now we can directly apply the m star app rule, which, if you recall, says that a string appended to another one will match a regular expression, a star of a regular expression, if the first string matches the regular expression and the second string matches the other regular expression. Okay, so why did we have to do this rewriting step here? Why couldn't we just apply this rule directly? What would happen? I'll process it, but. Right. So let's see we'll see what happens. Okay, so we get an error. Why do we get an error? Oops. So if you look at the conclusion of that m star app rule, it is very specific. It is expecting the string to be of the form one string appended to another one, right? And if the string is not of that form, this rule does not apply. They are not syntactically the same. And coq, in this case, is not smart enough to figure out on its own that appending nil to the end of the string is the same as produces the same value as the original string. So we have to do a little bit of massaging in order to apply this rule so that everything matches up as coq expects. So here, if we just, right, let me step out. We have to do this rewrite. We apply this, and we are Good, so now we have this as an assumption, we're done. And here we can use that extra special rule we added saying that the empty string matches regular expression star, always matches regular expression star, and we're done. Okay. So, do I want to do this? Okay, I'm going to try and do something a little bit on the fly here and see what happens. So, suppose we had done this instead. Suppose we say that we're just going to peel something off the end. Is this safe? I don't know. But no, I'm not going to do this. Never mind. I'll get into trouble. I guess I didn't try. Okay, so I apologize. I encourage you in your free time to try and switch those rules and see how the proof has to be adapted in order to make it go through. Okay. So, right. Naturally, if we have, because as we saw with even, when you have these inductively defined relations of propositions and you're reasoning about them, typically you're going to need some information about the subtree, the subtree that's used in the proof, right? So induction is often demanded for these inductively defined propositions, and X match is no different. Okay, so right, so here's one for you. If a regular expression matches some string S, then all elements of S must occur as character literals somewhere in RE. And this is precisely because we don't have any sort of wildcard operator in this regular expression language, right? So how are we going to set up this proof? So this intuitively makes sense, but in order to formulate this in coq, we're going to have to go through a couple of extra steps, right? We're going to have to formalize what it means for all elements of S. What are the elements of S, right? We're going to have to have some way of extracting those out. And then we're going to need to have some way of expressing what it means for a character to occur in a particular regular expression, right? So let's look at what fixed point RE chars is going to do. Well, it's just going to recurse over the structure of the regular expression. Every time it hits a char, it's going to add that to the list of literals. And then it's going to append things appropriately as it works on the subtrees. Yeah. In the case of what it means for a particular character to be inside a string, we're going to rely on the definition of in that we had from our previous chapter, whose name I can't remember right now. So we're going to use that. And because we're using that in, we're going to also rely on this fact that we had, that we proved in that chapter. I guess from logic. Here's the proof. It just says that if a element appears in two lists appended to each other, it must be the case that it either appears in the first part of the list, or it appeared in the second part of the list. And this intuitively makes sense, right? So now that we've done that, we can formulate precisely this informal definition we had before in coq. So here it says, if we have some string that matches a regular expression, and if there is some particular character that appears in that string, then it must be the case that that character also appears in the list that we got from running this character extraction function over the regular expression, right? And let's see how that works in action. There we go. So intros. Here we're going to do induction over the how this regular expression was built up. Okay, and we're going to get several cases here. One for each of our rules in this match proposition. I think most of these are relatively straightforward. The interesting case, of course, is, well, there are really two interesting cases. One where we use the char matching rule, in which case we're going to need to evaluate this RE chars function that extracts the characters out. So this is going to give us either x prime equals x or false, but from our definition of in up a simple in, this is precisely what we have up above, so we can apply it directly, and we're done. Another interesting case is where you need the sum lemma about when an element is included in two lists appended to each other. So right up here, right, we have as an assumption that either x was included in the first part of the string or the second part of the string that matched against this app regular expression. Okay, so now we can, oh right, so we're going to rewrite. I skipped over this part of logic, but it is possible to use the rewrite tactic to apply if and only if rules. So what's actually going on here is, if you recall that our in-app if lemma had the form if and only if. And so when we rewrite with it, if we have a goal or an assumption that precisely matches the left or the right-hand side of that if and only if, we can replace it with the other one, if that makes sense. So here we're going to replace this in x, two strings appended to each other, with the or. And it also is going to work down here in the conclusion. And if you want to see how that works, I encourage you to read in logic. There's a little section about settoroid rewriting that gives you more details on all the exact machinery. Okay, but once we have that in hand, we now know that either x had to be in the first part of the list, or had to be in the first string, or it's in the second string, right? And now we can just use our destruct tactic because we have an or, and that's going to give us two cases, one for the first one, one for the second one. And now we can just apply our inductive hypotheses using left to prove the left-hand branch of the conclusion and right for the other one. And then these other rules very much follow immediately, or these other cases very much follow immediately in a similar case. Oh, except this one, which is worth discussing, I guess. Right. So this is actually yeah, right. So what's interesting here is that now we get two induction hypotheses, which correspond to the two subparts of the M star rule. So if you recall, the M star rule said, A, the string had to match the regular expression. The first part of the string had to match the regular expression, and then the tail of the string had to match the star of the regular expression, right? So there are essentially two, the proof tree has two branches that continue to can continue to apply the rules for this inductive proposition to build up this evidence, right? And correspondingly, we get two inductive hypotheses, one corresponding to the branch on the left-hand side of the proof tree and one corresponding to the branch on the right-hand side of the proof tree. And we can use those. Here, this corresponds to the left-hand side, this corresponds to the right-hand side, and we can use those when we're proving this thing, basically. So there are two cases. One, it was either in the first part of the string or the second part of the string, and we'll use one of these induction hypotheses for either cases. So if it was in the first part of the string, we'll use the induction hypothesis for the left-hand branch of the proof tree. If it was in the second part of the string, we'll use the right-hand branch. And we're done. Okay. I need a drink. Are there any questions so far? Okay. That's worrisome. Okay. So the remember tactic. Okay. So there's one unpleasant thing about working with induction that and similar destruct that you may have come up across when you were working on your exercises, or may not have yet. But induction has, if you try and induct over a piece of evidence that isn't sufficiently general in the sense that it's talking about something that's too specific, it can lose information. And the best way to see this is to actually see what it looks like in action here. So here, what does this say? So this says that if S1 matches regular expression star, and S2 matches regular expression star, and then appending those strings together will also match regular expression star, right? So if we try and do induction over the first hypothesis, there's an issue here. And that is, whereas before we had this assumption that this string matched some arbitrary regular expression, here we're a little bit more specific, right? This says this is matching a particular regular expression, star something more general, right? And this is going to be problematic when we try and do induction. So it's best to just see what comes out. In the empty case, there's nothing particularly interesting. It works out as expected. The other cases are a little bit more problematic. So we're going to move to that next case. So what happens here? So here, we have to show that the second string matched some character x prime, and that x prime appended to S2 is matches char of x prime here. But this is problematic because we've lost this this bit of information about the star, right? The star that we had wrapping this original RE has completely disappeared. And in fact, if you look at the rules, there's no way to construct this bit of evidence, right? So if we pull in, or construct this conclusion. So if we do an intros and we do inversion on H, now we're stuck showing that x prime appended to x prime matches char of x prime. And this is clearly not false. There's clearly no way of building up this goal. Okay, so what happened here? Where did things go terribly, terribly wrong? So the issue is that when you do induction over a particular judgment, it only works if the values that are used in that judgment are completely general. So if they have the form, some constructor of that data type applied to some other things, that gets lost completely. That information just disappears along the way. And that's precisely what happened here. So, and the reasons for this have to go into how induction is set up and how it works under the hood. But we're not going to get into that. We're just going to see one way to work around it. So one way to work around it is to just force the thing we're inducting over to be completely general. And we can do that by just adding this equality, right? So we'll just say, oh, there's some new regular expression RE prime, and it's equal to star RE. And S1 is going to match this new regular expression. And now when we do induction over this, we actually have this equality in scope, and we can use that equality to do some rewriting, and the proof will go through. But as the slide notes, this works, but it's sort of ugly, and we're sort of complicating the statement of our lemma to account for some of the deficiencies in how the induction tactic works. So it turns out there's a better way to do it, which is the remember tactic, which is what we led with here. So the remember tactic is a useful tool to have in your arsenal when you're doing proofs by induction over these inductively defined relations. So what does remember do? Remember E as x does the following things. First, it replaces all occurrences of the expression E that you're remembering with some new variable x, and it adds an equation, x equals E, to the context. So in other words, if we're in this star app case here, and we say remember star RE as RE prime, we're going to get into the same proof state that we would have for that original uglier lemma definition that we had on the previous slide, this particular formulation of star app, right? And now, once this stuff is in scope, we have this extra bit of information in all of the inductive cases, which is going to allow it to work. So let's go to that proof right here. So here's star app again. We're going to do remember, and now we get this extra equality, and we get this new RE prime related to this the original RE. We're going to call generalized dependent to stuff some stuff back in the goal, so we have a sufficiently general inductive hypothesis. And now we're going to do induction over this more completely general match proposition, where there's no extra information encoded in the values that we're making a judgment on. So now when we do induction, okay, this case is not so interesting. But now, note that here in the mchar case, which is precisely where we got stuck, we have this extra assumption that character of x is equal to star of